Cathodic protection of buried pipeline is a technique used to prevent corrosion of pipeline by making the pipeline the cathode of an electrochemical cell. Cathodic protection of buried pipeline is a critical technique employed to combat corrosion, a major threat to the integrity and longevity of pipeline. This method involves utilizing the principles of electrochemistry to prevent the corrosion of buried pipelines, where they are particularly vulnerable to environmental factors such as soil chemistry and moisture. One common approach to cathodic protection is the utilization of sacrificial anodes. These anodes, typically made of a more reactive metal like zinc or magnesium, are strategically placed along the length of the pipeline and connected electrically. When buried pipeline, these sacrificial anodes corrode preferentially to the pipeline material, effectively sacrificing themselves to protect the pipeline from corrosion. Another method is impressed current cathodic protection, where an external power source is used to force a protective current onto the pipeline, thereby preventing corrosion. This method is often employed in situations where sacrificial anodes may not be practical or effective, such as in high-resistivity soil or in large pipeline systems. During the implementation of a cathodic protection system, various issues may arise that necessitate attention and suitable remedies. In this article, we will explore some prevalent problems, obstacles, and resolutions linked with cathodic protection, including electrical interference, uneven current dispersion, and corrosion due to elevated soil resistivity, among others. Electrical interference. Electrical interference poses a notable challenge in cathodic protection, stemming from potential stray currents originating from transportation systems or nearby electrical infrastructure such as power lines, electrified railway tracks, or communication cables. These currents generate electromagnetic fields that disrupt cathodic protection operations, hindering effective current distribution and compromising the system's efficacy. Involves implementing mitigation techniques such as meticulously designing grounding systems, employing conductive coatings, and physically separating electrical cables from cathodic protection systems. Regular monitoring of electrical interference is also crucial to promptly detect issues and implement corrective measures. Irregular current distribution. Irregular current distribution presents another significant hurdle, where achieving uniform current dispersion across the protected pipeline proves challenging. Factors like structural geometry, anode placement, and soil conductivity contribute to uneven protection levels. To tackle this challenge, meticulous system design is imperative, incorporating strategic anode placement and deploying current distribution components like cables and connectors. Install current distribution devices such as cables, bonds, and junction boxes to ensure even distribution of protective currents along the pipeline. Corrosion due to high soil resistivity. Corrosion stemming from high soil resistivity poses yet another obstacle to effective cathodic protection. In regions with dry or rocky soils exhibiting elevated resistivity, the slow dissipation of electrical current complicates adequate protection of pipelines. Addressing this challenge involves employing strategies like augmenting anode density, utilizing high-performance anodes, and enhancing soil conductivity via the injection of conductive chemicals. The optimal approach depends on specific site conditions and warrants evaluation by cathodic protection experts. limited coverage. Cathodic protection systems may not provide uniform protection across the entire surface of the buried steel object. Variations in soil resistivity, environmental conditions, and geometry of the pipeline can result in areas with insufficient protection, leading to localized corrosion. Evaluate the placement of sacrificial anodes or impressed current sources along the pipeline route. Ensure that anodes are strategically located to provide uniform coverage and protection to all sections of the pipeline, including bends, intersections, and areas prone to corrosion. Consider increasing the density of sacrificial anodes or impressed current sources in areas where coverage is limited or where corrosion risk is higher. This may involve adding additional anodes or adjusting the spacing between existing ones to optimize protection. Installation challenges. Proper installation of cathodic protection systems requires expertise and careful consideration of design parameters. Inadequate installation practices, such as improper placement of anodes or insufficient electrical bonding, can diminish the system's effectiveness and lead to accelerated corrosion. Ensure that the cathodic protection system is designed according to industry standards and guidelines. Risk of overprotection. Excessive negative potentials can cause hydrogen embrittlement or alkaline corrosion of the steel, leading to structural integrity concerns. Implement measures to control the output of cathodic protection rectifiers. This may involve adjusting the current output to provide sufficient protection without causing negative potentials that could lead to hydrogen embrittlement or alkaline corrosion. Implement hydrogen monitoring systems to detect any signs of hydrogen embrittlement resulting from overprotection. Negative potentials refer to the electrical potential measured at the surface of the pipeline relative to a reference electrode, typically a saturated copper sulfate electrode. Negative potentials are typically expressed in millivolts, MV, relative to the reference electrode. Commonly accepted negative potential values for cathodic protection of buried pipelines typically range between -850 mV and -1100 mV versus copper sulfate, although exact values may vary based on industry standards and project specifications. By recognizing the importance of these challenges and implementing appropriate solutions, can effectively mitigate corrosion risks and ensure the continued effectiveness of cathodic protection systems. Active maintenance and regular monitoring play a vital role in identifying issues early and preventing potential failures. With careful planning, attention to detail, and a commitment to ongoing maintenance, operators can overcome these challenges and safeguard critical infrastructure from the damaging effects of corrosion. Thank you very much for watching the video. You may consider to subscribe, like or sharing the video, if it is worth doing. Explore our YouTube channel, Petrosult, for captivating videos covering science, engineering, technology, and energy topics. The primary aim of launching this YouTube channel is to facilitate the exchange and dissemination of knowledge and experiences among professionals and amateurs.